All right, everyone. Today is day 2 of lesson 4.5. So today's main focus is going to be on rational inequalities, but we will see a couple extra examples for rational equations. All right, so here's just a refresher on the steps to solve rational equations. First step, we want to figure out what the least common denominator is between all of our fractions. Next step, we're going to convert each term into a fraction that contains the least common denominator. Next step, once we've got common denominators, we are just going to eliminate them. Then we're going to solve for our variable and make sure we check the solutions so that in case we've got an extraneous solution, we can account for that there. All right, so here's our first problem. First thing we want to look for is what is the least common denominator. Our first fraction has a denominator of a b plus 5, so that's one factor. And then our other fraction has a denominator of b minus 3, that's the other factor. Two different factors, we need one of each to make up our least common denominator. So our next step, we're going to convert each fraction so that it has the LCD. The first fraction was missing the b minus 3, so we're going to multiply top and bottom by that. And our second fraction was missing the b plus 5, so top and bottom by that. Next step, we're going to simplify the numerators. Now that our denominators are the same, we're going to eliminate them. And we're just left with the tops. So from here, we're going to solve for b and check our solution. So I started by taking away 3b on each side. There's the result. Subtract the 27 over. There's the result. And then dividing both sides by negative 12, we get a positive 1 for our answer. Plugging it back into the original equation and checking to see if it's valid, it does work. So b equals 1 is our solution. All right, here's the next one. Let's check out those denominators. We've got a factor of an x minus 2 and an x plus 4. So we need one of each for our LCD. Converting each fraction so that it has the LCD. Our first fraction would be multiplied top and bottom by x plus 4, second fraction by the x minus 2, and then the last fraction by an x plus 4. Simplifying the numerators, there's the result. Now that all of our fractions have the same denominator, we can go ahead and eliminate those denominators. Then from here, we're going to solve for x and make sure to check our solution or solutions if we end up with more than one. We're going to combine like terms on the left. And then we're going to get everything to one side because we ended up with a quadratic. So we need one side equal to 0. So we're moving the 6x term over and the 24 all in one step. And here's the resulting quadratic. From here, we're going to factor. So what two numbers multiply to negative 30 and will add to a positive 1? That would be a negative 5 and a positive 6. Solving for our x values, we get x equals positive 5 and x equals negative 6. Checking each of those, they both work. So both of them are our solutions. All right, next up, we've got solving rational inequalities. So these are going to have kind of a lot of steps and different steps than what we are used to working with. So make sure you guys go through these very slowly, rewatch them a couple times if you need to. Take really good notes on this section. First step, we are going to find the excluded values for our rational expression. And we're going to get that by setting the denominator equal to 0. And then we're going to also find our 0 values, which we'll get by setting our numerator equal to 0. Our next step, the values that we got from step 1, we're going to plot all of those on a number line in chronological order. The excluded values are always going to have an open circle on the number line because we want to exclude that value. The zero values, though, that's going to be based on the symbol. So if we had an or equal to type of inequality, it'll be closed. If we didn't have the or equal to portion, it's going to be an open circle. Then after that, we're going to test the intervals to determine if an interval is a positive interval or a negative interval value. Then based on the inequality that we were given, we're going to determine which of those intervals we want to choose as our answer. So whichever ones will make the inequality true. All right, here's our first rational inequality. We've got an x squared minus 16 over an x plus 6. And our inequality is greater than 0. Our first step, we're going to factor top and bottom. The top will factor because it is difference of two squares. It's going to factor into an x plus 4 and an x minus 4. The x plus 6 on bottom is already in factored form. We can't do anything else with that. So now we're going to find both the excluded values and our 0 values. So first, excluded values we get by taking the denominator, in our case an x plus 6, and setting it equal to 0, and then solving for x. So our excluded value is -6. And that's going to be an open circle. Excluded values are always open circles on the number line. All right, next we've got 0 values. We're going to get those by taking the numerator and setting them equal to 0. So we've got two different factors in our numerator. X plus 4 equals 0, x minus 4 equals 0. So the two 0 values that would make that entire expression equal to 0 would be an x value of -4 and an x value of +4. And because our original inequality was just a greater than symbol, we didn't have the or equal to portion, our 0 values in this case will also have an open circle. All right, next up, we're going to graph our excluded values and 0 values onto a number line. So here's where they would end up. Next, we got to figure out which of those intervals, now that our number line has been separated into intervals, which of those 1, 2, 3, 4 intervals are going to be our solutions. So we want intervals that are going to be greater than 0. And I'm getting that from the original inequality again, because our expression had to be greater than 0, have a value more than 0, which means we're looking for the intervals that are going to have a positive value. In order to test to determine which intervals are positive versus negative, we are just going to start with a test value. So we're going to test the value of x equals -7. And the reason I chose that is because it's to the left of -6. So -7 is to the left of -6. So I'm testing this first interval, the one that's going off towards -infinity. And I'm going to test that by plugging -7 into my rational expression that I started with. So replacing my x's with a -7, evaluating the numerator and denominator, and then dividing. It evaluates to give me -33 as an output. So because I got -33, that means this was a negative interval. So that entire interval to the left of -6 is going to have a negative value. So any of those x values that I plug in to the left of -6, when I plug them into my rational expression, I am going to be getting negatives every single time. Then what's cool about this is that once you figure out that first interval, the rest of them are just going to alternate positive, negative, and positive. So now that we've got our interval positives and negatives determined, our focus, our answers are just the positive intervals. Those are the only ones we care about because those are the solutions to this inequality. So that's going to be the ones that are highlighted. So between -6 and -4, that was a positive interval. And then the one that is greater than +4. And those are my solutions. So the first solution, X is between -6 and -4. And then also my other solution, X is greater than 4. All right, here's our last one. We've got an x squared plus 3x minus 18 all over x squared minus 3x minus 10. And that rational expression is less than or equal to 0. First up, we're going to factor the top and the bottom. Our numerator factors into an x plus 6 and an x minus 3, because the two numbers that multiply to -18 and add to +3 are 6 and -3. Then our denominator factors into x plus 2 and x minus 5, because the two numbers that multiply to -10 and add to -3 would be 2 and -5. Next up, excluded values. We'll always get those by setting the denominator equal to 0. X plus 2 equals to 0, x minus 5 equals to 0. And so that gives us excluded values of -2 and +5. Excluded values will always be an open circle on the number line. Then we've got our 0 values, which is taking the numerator and setting it equal to 0. So our x plus 6 equal to 0, x minus 3 equal to 0, gives us 0 values of -6 and +3. This time our 0 values are going to have a closed circle because our original inequality was less than or equal to. So because we had the or equal to portion, that circle, those circles are going to be filled in. Let's plot them on the number line. Here they are. And there's our corresponding circles, open and closed. Next, we want to figure out what of those intervals are going to be our solutions. We want intervals that are less than or equal to 0. And again, we're getting that from the original inequality. So less than 0 means that we're going for negative intervals. So let's test our first interval. And again, this is just coincidence this time. We are testing -7 again. Again, totally a coincidence that it was -7. And the reason that is because our leftmost point was, again, at -6. So we want to test something to the left of -6. So -7 is perfect choice. We're going to plug that in to our original expression, okay? So plugging that -7 in for our x's in the top and the bottom, here's what that looks like. And then evaluating from there, we get approximately 0.17. It ends up being 0.16 repeating. So because that value ended up being positive 0.17 approximately, that means our first interval that was to the left of -6 was a positive interval. Anything to the left of -6 that we plug in to our expression will give us a positive value out. So we're starting with a positive interval, and then we're just going to alternate after that. Negative, positive, negative, positive. We are only interested in the negative intervals. So our solutions are going to be between -6 and -2. And +3 and +5. So here's how we would write our solutions. Now be really careful about the inequalities that you use to show between -6 and -2 and 3 and 5. At -6, we had a filled in circle or a closed circle. So we have to have the or equal to symbol. And then same thing with 3, it was closed. So we need an or equal to there as well. So there's our two solutions. All right, that is it for today. So after today's lesson combined with yesterday's, you should be able to complete all of the 4.5 homework. So let me know if you have any questions, but when we come back from our little fall break here, we will be preparing for our test. So 4.5 homework for today. And just a heads up, your test is going to be next week, Wednesday. Hope you guys have a great break, and I will see you on Monday.